All right, guys, we're going to learn how to predict products on this short video. So you have to remember what our types of reactions are, because that's really going to help us determine kind of what happens here, right? So remember, our options are it's precipitation, right, which is sort of like a double replacement. It's an acid base, right? Or it is a redox. And redox includes usually synthesis, decomposition, and like single replacement. Okay? So the easiest way to do this is to just do some, right? So I have a handful, I think I have 5 or 6 here examples. We're going to go through, I'm going to kind of talk you through how to do it. And then there's a worksheet posted where you can try to see how many of them you can get, okay? So let's give this a go. Let's give an example here. First example I want to give you is this, okay? So it's lead nitrate, or lead 2 nitrate, I should say, and potassium iodide. And this is all you're given, and you're asked, what are we going to get? Okay? Sorry, this is aqueous as well, but you can look that up with your chart. The question is, what are we going to get, right? Run through your possibilities. So if you're not sure, just kind of run through it, right? So is there anything that it probably isn't, just based on what we see? And hopefully you're thinking, well, it can't really be acid base because there's no hydrogen moving, right? There's no hydrogen moving, okay? And if you're looking down at redox, redox is usually synthesis, like combining everything, which, I mean, I guess that could happen here, but this would be kind of a hot mess of a substance if you put all of these things kind of smushed together. I don't know that that would work out very well, but I suppose it's possible. Decomposition doesn't really make sense, right? Because that usually is like one big thing breaking into pieces. Single replacement doesn't really make sense because we'd have to have something sort of on its own, and we have 2 compounds already. So really all that's left is a possible precipitation, okay? And remember, precipitation is like double replacement, where you start with 2 ionic things and they sort of switch partners, right? So if we're going to guess precipitation, which it seems like is the most logical at this point, now we have to actually make the products. So first thing that I'm going to do is identify kind of what thing could go with what thing, right? So right now, lead is with the nitrate. And in this, lead is the positive one and nitrate is the negative one. And over here, it's that. Now, what specifically are the charges? Because that's going to come into play later on, right? So potassium is a +1, iodine is a -1. Nitrate, if you look up on your chart, should tell you -1. If you know that, and you know that there are 2 of them, then the lead here must be +2, okay? So who can switch and go with who? So positives aren't going to go with positives, they're going to repel. Negatives aren't going to go with negatives. So the only option will be now lead is going to partner up with iodine. And potassium is going to partner up with nitrate, because that's really the only option that we can do here. So now we have to figure out how they fit together. We have to make the compounds how they exist in life, not by just smushing together what's there. So if I put potassium with nitrate, how do those fit together? Potassium is a +1, nitrate is a -1, and so they actually just fit together nicely 1 for 1. So I should have just written that out. Okay, that's how potassium nitrate exists in the world. Now you might be thinking, well, there's 2 of them over on the left-hand side here, right? How am I going to deal with that? Well, the answer is when we're done, we will balance this equation and we will handle that later. Do not carry subscripts over. If they're the same on one side to the other, that's a coincidence, okay? So we'll worry about the numbers of things later. Just make the compounds how they exist in nature. So now we're going to go over and we're going to look at lead and iodide. Lead is a +2 and iodide is a -1. So I'm going to need 2 of those. Okay. Then you are going to go to your cheat sheet. So let me switch over to that real quick because we need to know if one of these precipitates out. So if we pull this back up and we pull up our reference sheet here real quick. Here we go. Right, so all nitrates are soluble. So that the KNO3 should stay soluble. And now we got to look for iodide, lead iodide. So all of them are soluble except when with lead. Okay, so going back, that means that this one is aqueous and this one is solid. So we have just confirmed that not only is this the reaction, but it is also, yes, a precipitation reaction because a precipitate was formed. And what's the last thing we do? Well, now we can balance based on what we have here. So we have these 2 nitrates over here. I need to make 2 of them over here. And then I have 2K and I have 2I, so I'm going to do that. And that should give me my answer. Okay, so you see how that works? You got to kind of walk through your options, kind of like by process of elimination. What are the possibilities that could happen? And then make the compounds the way you think they exist in life, and then go back and balance the equation, and you're done. Okay? Let's try another one. Okay. So again, sorry, let me just write this down. This was precipitation. Okay. So we got options here. What do we think is going to happen? So precipitation's kind of out because that requires us to have 2 ionic substances in the beginning, and we don't. We only have the 1, so that's kind of out. Acid-base looks like it's out because there's no hydrogen, so this kind of leaves us to redox, right? But more specifically with redox, I think it's going to be a single replacement because it's not going to be decomposition because that would, again, require more pieces, and that doesn't necessarily make sense. It could be synthesis, but rarely do we see a compound where there be more than 1 metal in it. So I don't think silver and copper are going to mix well together. So I think single replacement is the best option here. So that means that silver is going to kick somebody out of the compound and take its place. So is silver going to kick out the copper, or is it going to kick out the chlorine? And the question is, well, what is silver like to do, right? Silver is a metal. So it's going to take the place of the other metal, right? Silver likes to take on the positive charge. It's going to take the place of the other positively charged thing. So that means we're going to be left with copper by itself. And you have to ask yourself, can copper exist by itself like this? Or does it need to be kind of like copper 2 or Cu2, things like that? You know how some elements have to do that? Copper is a metal, so metals can in fact exist on their own, and they usually do so in the solid form. Then I'm left with silver and chloride. This one's a little tricky because silver is a transition metal. You may not know what charge it will take, so it might be hard to kind of predict the formula. So I'm just going to tell you that silver tends to take a +1 charge. So if that's the case, we're going to end up with silver chloride, and if it's a +1, then we only need 1 chloride to do that. Okay? Now you can look at your solubility chart and you'll see that this is actually also a solid as well. So this probably, may not actually happen in real life this way, like nothing might actually happen, but for our purposes, we're just going to walk through and assume it does. So now we have to address quantity. I need 2 chlorides, which means I need 2 of the silver. And this is redox because charges have changed, right? Copper went from a +2 here to a 0. Silver went from a 0 to a +1. So silver was oxidized and copper was reduced, right? Silver's charge went up, copper's charge went down. So I would say that this is a redox. Okay, you could also call this a single replacement. Okay, let's try another one. Okay, and feel free to kind of pause these at any point if you want to try it on your own first. Okay, so here we have HNO3 and we have LiOH. So we got to run through the options again, right? This doesn't look like redox because, again, that means we would need to have kind of something sort of as it's on its own, like an element on its own kind of thing. And we don't see that. So could be precipitation, could be acid base. Okay, but we want to kind of see what happens here. So could any of these be an acid? You should ask yourself that, right? Could any of these be an acid? In other words, do any of these have a hydrogen that it could give away? And you should be saying this looks like it could be something that could give away a hydrogen. Okay. Little tip: if the compound starts with hydrogen, that's usually telling you that it is an acid or could be an acid. Okay. Okay. So if we think this might be an acid, we got to kind of think, all right, well, what would the products be? Products would be water. So in other words, the H from this thing would come over and be taken by this, and we would get water. And then what? Well, whatever's left would be the resulting salt, which would be lithium and nitrate. So now the question is, how do those things go together? Lithium is a +1, nitrate is a -1, so they go together perfectly. Okay. Water is a liquid, and this is aqueous. And it's balanced already, 1 for 1, so it's good to go. If you didn't pick up on the fact that this was acid-base and you thought maybe it was precipitation, which is also a good idea because there are two aqueous compounds that look like they might be able to kind of switch partners, you can almost think of acid-base reactions as sort of their own version of a double replacement kind of thing, except instead of producing a precipitate, we produced liquid water, which sort of took that role. But it's the same kind of concept where they sort of switch places, right? The hydrogen kind of switches partners here for that. Okay, but I think acid bases tend to be the toughest to kind of pick up on there. But again, just try some stuff, right? Trial and error and see how it goes. Okay, let's try a couple more here. Okay. We have hydrogen, H2, which is usually in the gas phase. And then we have bromine, which is usually in the liquid phase at room temperature. Okay. What are the possibilities? Check off the list. Is this precipitation? Hopefully you're saying no. Is this acid-base? Probably not. There's hydrogen there, but it's not a compound that has a hydrogen to give up, so to speak. It is like hydrogen kind of like in its elemental form. So it doesn't really look like acid-base would work. So that leaves us to redox, and redox has those kind of 3 different options, right? So we can be synthesis / combination. We can be decomposition, right? One thing breaking up into smaller pieces, or we could be single replacement, which usually means we have to have a compound in there somewhere to drop something. So which makes the most sense? I think combination actually seems pretty reasonable, right? These are both things in their sort of elemental form. Remember the Brinkelhoff elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, that when they're in their quote-unquote elemental form, they are in their diatomic form, right? Diatomic. In other words, H2, Br2, Cl2, so on and so on. So these things are basically in their elemental form. So if we think that they're going to synthesize something or combine to be something, what would be that thing that they would combine to be in? So you might just say, oh, well, let's just squish them together, right? H2Br2. No, don't do that, okay? We will deal with how many things there are when we're done and after we balance. Make the compound that you think would exist in real life. If H and Br formed a compound, how would that go? Well, Br tends to be a -1 charge when it's in a compound. H tends to be a +1 when it's in a compound. So they are going to form HBr. And you may not know the state of matter of that, which is fine. Don't worry about that one if you don't know. Okay, acids are typically aqueous, so I'll just put that in there. But okay, so now we can balance. Now we can address that the numbers are off by simply doing that. Okay, so we would call this one a redox / a synthesis, right, or a combination. Okay, let's try one more, and then I'll let you guys try some on the packet. Aluminum oxide, solid. What are our possibilities? Can't be precipitation. Can't be acid-base. It's got to be redox. So of the redox, what could we do, right? I think decomposition makes the most sense because we only have one big compound. There's nothing else to react with it. So really the only thing it can do is break into its pieces. So then the question is, what are those pieces, right? So we have aluminum and we have oxygen. So you got to ask yourself, can aluminum exist alone in its elemental form? And we should be saying yes, because it's a metal. So aluminum can just exist, aluminum. How does oxygen exist in its elemental form? O2, because of Brinkelhoff, right? So this is what it's going to turn into. And now the question is, okay, now we have to balance, okay? And to balance this out, okay, we have a problem with the oxygens, right? So we have an odd number on the left and an even number on the right. Best thing to do is to kind of think like fractions. If I have 3 on one side and 2 on the other, let's make them both 6, right? So then I can do that. And then I can fix the aluminums and do that, okay? So hopefully that gives you a little bit of a sense on how to approach this. I very much take the mindset of process of elimination because it doesn't always just come to you as to what you think is going to happen. Okay, so that's the first thing, process of elimination. Second thing, make the compounds how they exist in life based on everything that we've done this year. Don't worry about numbers until the end, and then you can go back and crunch the numbers. Okay? So hope that made sense. Check out the worksheet posted, and we'll talk more about it after the weekend.